Welcome back to Advent of Code 2021. Day 19. Alright. Yeah, just a few days left. One whole week. Beacon scanner. Oh yeah, so this one, look, we took a peek last time. It looks like a geometric kind of problem. As your probe drifted down through this area, it released an assortment of beacons and scanners into the water. It's difficult to navigate in the pitch black I'm going to skip ahead a bit. Each scanner is capable of detecting all beacons in a large cube centered on the scanner. Beacons that are at most 1,000 units away from the scanner in each of the three axes have their precise position determined relative to the scanner. 1,000 width, 2,000 width cube. It's actually 2001 width cube, but you just think of it as 1,000 away from the center. Wherever scanners cannot detect other scanners. Alright, so we've got some input is wait, what? Okay, so we've got a list of beacons that each scanner can detect. I guess. Okay. So if it's at that coordinates and there are beacons there and there, then the scanner could report that the first beacon is at that relative to the scanner, but would not detect the second beacon at all. Right. Unfortunately, while each scanner can report the positions of all detected beacons relative to itself, the scanners do not know their own position. You need to determine the position of the beacons and scanners yourself. The scanners and beacons map a single contiguous 3D region. This region can be reconstructed by finding pairs of scanners that have overlapping detection regions, such that there are at least 12 beacons that both scanners detect within the overlap. By establishing 12 common beacons, you can precisely determine where the scanners are relative to each other, allowing you to reconstruct the beacon map one scanner at a time. Alright, but I thought these beacons are given as relative coordinates, not global coordinates, universal coordinates, whatever. Well, we'll read on. Alright, so in 2 dimensions, we have this. The scanner O sees it like this. Okay. That's what scanner O sees. Scanner 1 sees that, fine. Relative coordinates. For this example, assume scanners only need 3 overlapping beacons. Then the beacons visible to both scanners overlap to produce the following complete map. Oh, these are the same beacon? Okay, that would make things a lot clearer. They're all talking about the same... Oh no. No, they wouldn't, because some beacons are not visible. So it's not necessarily... What is it asking though? Not sure yet, but they're not really saying what these lines are. Let me look at that again. The submarine has automatically summarized the relative positions of beacons detected by each scanner. Okay, so it's arbitrary beacons. It's not necessarily the same beacons. So in this example... Is that... Oh, 1 hour, wow, okay. Is that the longest yet? So this is implying that, well, okay, assume scanners only need 3 overlapping beacons. Then the beacons visible to both scanners overlap to produce the following complete map. I don't understand this assumption, like, they only need 3 overlapping beacons in order to... I mean, are they saying that every pair of scanners have 12 beacons in common? I don't really understand this paragraph. If we knew that these 2 scanners had 3 beacons in common, then we would know that those are the same beacons. And not necessarily in order. So that one is not... Yeah, so the order isn't the same, but the shape... Yeah, okay, if we knew that they had 3 in common... I don't really understand that assumption, though. That doesn't immediately seem to fall out of that paragraph there. It says... finding pairs of scanners that have overlapping regions, but we don't know... Okay, I'll read on. Find the common beacons first. But that's impossible. Like, it's all relative. Like, for all we know, these could be like a long way away from each other so that there's zero overlapping. Unless there's more stipulations, but unfortunately, there's a second problem. The scanners also don't know their rotation or facing direction. Due to magnetic alignment, each scanner is rotated some integer number of 90-degree turns around all of the X, Y, and Z axes. That is, one scanner might call a direction positive X, while another scanner might call that direction negative Y. Two scanners might agree on which direction is positive X. One scanner might be upside down from the perspective of the other scanner. Okay. So it could be in any of 24 different orientations. There's 6 different facings. And for each of them, there are 3 different axes that consider the up direction. We used to have to respect that. What was it? The left-hand rule? The right-hand rule? I forget now. There's one for one thing and one for another thing, which... Well, alright. Here is an arrangement of beacons as seen from a scanner in the same position but in different orientations. Okay, so basically the axes are shuffled. By finding pairs of scanners that both see at least 12 of the same beacons, you can assemble the entire map. For example, considering the following report. Because all coordinates are relative, in this example, all absolute positions will be expressed relative to scanner 0. Scanners 0 and 1 have overlapping detection cubes. Why? The 12 beacons they both detect are at the following coordinates. What? Just compare if they share 12 values. I still don't understand. Are they asserting that they do share 12 values? Then that's knowledge we know. Or are you trying to find if they share 12 values? Because if it's the latter, that's still impossible because it's relative positions, not absolute positions. The 12 beacons they both detect are at the following coordinates. -618. So -618 was relative to scanner 0, so it should appear in this list. What? Well, I don't see a -618. At the following coordinates. I don't see these in scanner zeros. So we're taking absolute here to mean relative to scanner 0. I guess with distance matrices. This is poorly explained. I don't think it's... This paragraph is the most confusing one. These examples don't... Right, if we go back to the simplest 2D example... Assume scanners only need 3 overlapping beacons. Hang on, so... Yeah, still, these don't appear. Okay, 618, did it appear in the other axes? Maybe it was a different axis. Okay. Oh, it was there, I didn't see it. Okay, it is actually there. Minus 618, minus 824, minus 621. Okay, fine. So those are actually in scanner zero's set. All beacons they both detect are at the following coordinates. So it's minus... Where you could compare Manhattan distances with each scanner. So it shouldn't... Minus 618. I wouldn't expect to find it in scanner 1 because it's like... not relative. So let me just check if it's actually there. No. Okay, fine. So... Alright, so they seem to be establishing that it's a fact that every pair of scanners has at least 12 beacons in common. If that's true, then I guess there is some... Okay, fine. Then I guess you can deduce by some process that it must be these 12. I'm not sure how yet, but I guess that's the part of the problem. Like, and then if you knew... Okay, so let's assume we knew how to do that. I don't think every pair of scanners has 12. But you have to find the ones that do. What? So they either do or they don't? And then we know nothing. I'm so confused now. Then we have absolutely nothing in common between these scanners. Like, how can we possibly know whether whether a beacon is the same in one than the other? Like, they could be like a million spaces away from each other. Like the small example. I mean, the small example, this could be in one region of space, and this could be in a completely other region of space. They could be completely separate beacons. Or they could be in the same space, and they'd be the same beacons. Like, I don't see any information that can tell us whether they're the same beacons or different beacons. I don't understand how this falls through. Like, why is it necessarily the case that these... It's telling you how it works. I mean, did they tell us how many beacons there are? If we knew how many beacons there were, maybe we could narrow it down. Yeah, I don't even get the small example. Like, what? There are an unknown number of beacons in existence. Scanner 0 sees 3 of them. Scanner 1 sees 3 of them. So we know there's a minimum of 3 beacons in existence. And it's a maximum of, well, unlimited, because there could be others that they can't see because they're further away. So given just that information alone, that's all we know. Assume scanners only need 3 overlapping beacons. Finding pairs of scanners that have overlapping detection regions. So how do we find... Okay, we know there's only 2 scanners in existence in this example. So it says we're trying to find pairs of scanners that have overlapping detection regions. Are they basically saying there definitely exists at least one such pair? But they're not actually saying that. What you have to find is matching distances between beacons, if I'm not misunderstanding. Yeah. I mean, that's if we know that two scanners have beacons in common. X number of beacons in common. I still don't understand which pairs of scanners have beacons in common, and which, like, does every single pair of scanners have 12 beacons in common? Is that what they're saying? All scanners are mapping the same region. Yeah, but they don't cover the whole region. No individual scanner covers the whole region. So they could all be close together and have a lot of overlap, or they could be far apart and have very little overlap. Huh. So they say it's contiguous. That means scanners are necessarily connected. Like, every scanner is gonna overlap with at least one other scanner. Okay, that's probably true, but they could be in a line and just touching, their regions are just touching. So they could be in a line, or they could be kind of all clumped together. They could even be in a donut shape with a big hole in the middle. Or you can find the ones that have 66 matching distances between beacons. 12 choose 2. But even if there are matching distances, it doesn't mean... Like, it could just be that there are a bunch of beacons that have some pattern of matching distances between them, and that exact pattern happens to be seen elsewhere. So it doesn't mean they're the same beacons, does it? Like, like in the most extreme example, if we're assuming they have to be contiguous, Yeah, I mean, it's possible for these regions to be contiguous, but no beacons overlapping whatsoever. That's also possible. You literally just line up the cubes next to each other and just have each of these literally the cubes are just touching on the corners or something, or just on the edges. So each of these could be completely separate beacons, and no two are common. No two are the same. That would technically meet the specifications here, I would think. Like, I don't see anything that prevents that from being the case. Ideally, you'll find a lot more than 66, so you'll be sure that more than 12, since you don't care about the exact number of matches. Like, okay, this example. Okay, this sentence here. Scanners 0 and 1 have overlapping detection cubes. Where does that come from? How do they know that? Like, they said it's contiguous region, but that doesn't mean 0 and 1 are connected. It could mean 0 is connected to 3 and 3 is connected to 1, like in a line. So what led them to believe that scanners 0 and 1 have overlapping detection cubes? And then it says scanner 4 overlaps with scanner 1. Why 4? Why have they jumped to 4 now? What happened to 2 and 3? I don't know, none of this makes any sense. 2 and 3 don't share 12 beacons with the others. Why? How do we know any of them share any with any? I don't get where they got the first sentence from. Like, these are just arbitrary numbers. Like, why is it any more likely that 0 and 1 have common beacons than 1 and 2 or 2 and 3? That's what you have to figure out. Well, I don't think it's possible, according to my understanding. Like, these... Like, according to the description, these could be cubes that are just next to each other. And these could all be beacons within those cubes, respectively. So I would think that these could be completely different beacons, none of them coinciding, and it would still meet the description, wouldn't it? Like, they didn't say anything about how many they must have in common or anything, they just... So I would think it's possible to have 0 matching beacons, and that's a valid layout of these coordinates. But are they just like... They're just choosing 0 and 1 to have overlap? But they wouldn't have given you an input like that. But no, I'm saying for this input right here, these could be separate cubes. Like, what, it's just, they're all relative coordinates. Why, how is that any less likely than showing you the exact coordinates that match after that? But, what, this? But these don't match, because let's say that triplet there, that's in scanner 0, because they've decided scanner 0 is the origin. But that's not in scanner 1. (618) matches with 686. Yeah, but we could say this matches with like that one. Or we, well, okay, no, that wouldn't work, because then the others wouldn't match up. But we could say that it doesn't match with 686. Like, we could say that they literally don't match up at all. I don't get where they got this sentence from. Like, what's stopping scanner 0 and scanner 1 from being, like, I don't know, 5,000 units apart, and none of these actually match? Basically, it's a single cube with 79 beacons. But they didn't say... They didn't tell us how many beacons there were. All we know is the minimum at the end. Yeah, but that's not in the input. How can they deduce that? Like, the minimum number of beacons must be... say, this number of rows. Or, I don't know, I guess whatever the most number of rows is on any one of these scanners. It tells you it's 79 always, does it? Oh, that changes things. Where does it say that? The ends. Total there are 79 beacons. Oh, I thought this is for the example. Wait, is it? Yeah, no, they're saying that's the conclusion of the example, yeah. Not... Yes, that's the conclusion, but I mean, I don't get it. I could argue that I could say that every single one of these beacons is unique. In which case the number of beacons is that number plus that number plus that number, that number, it's that number, which is more than 79. Like, what's stopping that from being a valid interpretation? Hmm. How many are there anyway? Okay, so what's... And this number 12, what's special about 12? They're saying if you knew that a pair of scanners had 12 beacons in common, then you would be able to work out. Start with the example input and try things until you get 79 as a result. But still, I mean, I just gave... Like, I just gave an interpretation where 79 wasn't the result. I'm just trying to figure out why that interpretation is wrong. I still can't find any reason why it'd be wrong. Like... Why can't these all be completely distinct? What is the factor that's stopping them from being distinct? They said something... They said this thing about 12. I still don't fully understand this paragraph. But nothing in this paragraph is saying there must be any overlap at all. They just say find pairs of scanners that have overlapping detection. Okay, so they're asserting that... I think they are implying that there must at least exist at least one pair that has at least 12 beacons in common. Maybe that in itself is an important piece of information. They don't actually say that, but okay, so we'll assume there exists at least one pair with 12 beacons in common. Is that enough information to then for everything to fall out? Maybe. So if we know that there's these 4 scanners, and we know some pair of them has 12 in common, is that all the information they use to get to this sentence? To get to this conclusion, that 0 and 1 have 12 in common? Maybe. I don't know. Like... I guess this does have to be true, that there is at least one pair, because otherwise... This... Okay, yeah. So is that all the information you need to be able to deduce everything? It's telling you it's a cube of 1,000... 1,000 by 1,000 or something. Yeah. No, that's... Each... What do you mean? Each scanner's visibility is like a cube of 2,000... Technically 2001 by 2001, I think. In the example, it's using scanner 0 as the base and rotating the others until they match. But this still comes back to the fact that they may not match at all. They could just... Okay, I mean, if we know that there definitely has to be one other scanner that has 12 in common with 0, then yeah, I guess that's true. We can if we know that for a fact, and that seems to be established, then yeah, we probably can. How big is the input anyway? So there's 27 scanners, and all we know is that at least one pair amongst these scanners have 12 in common. I Maybe it's more than that. Maybe it's the case that every scanner has at least one other scanner that has 12 beacons in common with it. That allows us to start at 0. And then we have to figure out whether it's 1, 2, 3, or 4 that has 12 in common with it. And find the 12. So that they're saying these are the 12. And that tells them where scanner 1 is. And then from 1, they're trying to find what overlaps with 1, and they're saying 4. And then that finds 4, and then from 4, or following this process. Okay, so it's not necessarily from 4. 2, they find that 2 is here, but we don't know which of the scanners 2 overlaps. They haven't said, but... So 0 connects to 1, 1 connects to 4, and then 2 connects to one of those, 0, 1, or 4, and then 3 connects to one of all of those. That's the minimum amount that we can really deduce from this. Okay, fine. We can try and repeat that. So we can start at 0. We can assume that it has 12 in common with one of the other. Because once we have found that scanner 1 has 12 in common with scanner 0, And we can basically merge them together and say this is now just one big rectangle, one big cuboid with a list of beacons. Well, that actually makes it harder, because then it's a bigger set, and you're still sticking with 12 beacons, so that's probably not... You probably still want to keep them as separate sets. But just try and find 12 in common with 0 and something, or 12 in common with 1 and something. Alright, well, I mean, we could try and code a process that, given to lots of these, try and find if 12 of them match or not. Try and find if it's possible for 12 to match. And if the answer is yes, it's possible, we'll just assume, okay, then they match. Because in theory, it could be coincidence that 12 beacons just have the same distance pattern, but they don't actually coincide. But I guess we'll just have to assume that's so unlikely that it's not going to be the case in the input. And the facing and direction thing basically means that these columns can be swapped about, and the sign can be changed from positive to negative. So that's basically 6 permutations of columns times wait. They said there's 24 different orientations. But it's not just all the permutations, because some of those are invalid, because it wouldn't... it has to be like orthogonal rotations or something. Um... this is 1, 2, 3, 4, 5 examples of orientations, but I guess there's actually 24 different possibilities. How do we get all 24? Do we just... So each of... Isn't there an algorithm for this? Cabsh? Oh, maybe I don't remember this stuff. We can't just do every possible permutation of columns and every possible positive or negative of each column, because that would be too many, wouldn't it? That would be like 48. Only half of those are valid. What's Cabsh? I don't think this, this doesn't... Oh, I see. P and Q, two sets containing n points. To find the transformation from Q to P. Both sets of coordinates must be translated first, so that their centroid coincides with the origin of the coordinate system. I don't know if we have enough information to be able to use this. Also, I don't really understand it, but I don't think we would need it though. The process of finding, if we restricted to just finding like 3 points that match and just assume that that's like likely the likely a subset of the 12, if they do match, then that's probably not too hard. So if we just like restrict to finding like 3 points such that their distance pattern matches, and then work from there, just continue to add a point every time it does. That would probably be the easier process. How many we got here? 1, 2, 3, 4, 5, 6, 7, 9, 10, 12, 13, 14, 15, 16, 17, 22, 23, 24, 25. So it'd be like 25, choose 3, 1,300. Okay. So if we try every triplet, and for such a triplet, try every triplet in the other one. So we multiply those two together, so we're in the millions. And then for that pair of triplets, if we want to work out if they match, you have to do what exactly? You'd have to... If I wanted to work out if these three match these three, I would have to look at the interpoint distances, of which there are 1, 2, 3. And just see if that's a permutation of the other three distances. Would that be enough? And if the answer is yes, then what? We'd have to try and build that up to 12. But okay, so at that point we would know... Man. About an hour in, I haven't started coding yet. Well, I can try doing that at the very least, seeing how often that actually happens, that 3. Wait. Okay, but it's not enough to say... You've got to factor in... How many of your leaderboard friends finish this? What are we on? 19. 5 people. Well, I can start with that and see how often that actually happens, that 3 common to both. And then there's 27 scanners, so... Yeah, I think this might be one where I just have to just try a little bit here, and then I'll just have to think about it offline and try and understand the bloody description. Alright. This is part 1. This is crazy. This is literally the first time I can ever remember a problem where part 1 was just not... could not be comprehended. I still think it's just a really bad description. Lack of mathematical language used. Which I know that he tries to avoid mathematical language, just so that people understand it, but this is a case where it would have made it clearer how to use mathematical language. I mean, I think it usually is clearer when you use mathematical language, but alright, well, I'll just code something. Let's copy this in. At least parse the input. That's a start. Alright. Yeah, so these are in order, right? Okay, so then we could just... Alright, so let's just say... Okay. If not line dot strip, then just skip that line. If line dot starts with alright, just create a list called beacons. If line dot starts with that, then we just append what we have into the scanners. And then beacons is refreshed. Otherwise, we probably want to use... Do I want to use a pos class? The problem is the pos class specifies X, Y, and Z, and in this case it's actually indeterminate. Just put it as a triplet of numbers. beacons dot and say tuple of comma it's all empty. What's going on? Line in f.read lines. Here. So we've beacons.append tuple line.split what's the problem? Also, I probably have to finish soon, so I don't think I'll really get any logic done. Okay, we've got beacons. Oh, whoops, that should be outside the... no. Yeah, but why is that one empty? Oh, I see. Oh, no, this is the wrong way around. Not gonna do the last one. I need to... Alright, just do it like this. If beacons is not none, put it on, and then the end of this process we'll just have to do alright, let's check we've got the right number. For I row in enumerate scanners print I row 0 to 27. What? That's too many, isn't it? Oh no, it does start at 0. Yeah, it does. Okay, good. Alright. So we parsed the input. There's nothing small I can do now. Like, if I do any logic, I'm gonna have to dive right in. I don't particularly want to. I need to finish soon. So, yeah, the idea was to find, like, triangles that match, and then build up from there. And the thing about the axes is confusing me, because I don't know exactly the process of all the rotations, but I'll just have to look it up. There's there's probably just a series of matrices you could multiply to get every possible valid rotation. Because you can't just compute all permutations, because that'll give you 48. That's twice as many as you need. So half of those are don't respect the what's it called, the left-hand rule. So yeah, like yeah, and I can also probably offline. I could probably check the forums, see if anyone's actually explained this problem in plain English or mathematical English, because this, I still maintain, this is a terrible description. And I would say technically wrong, because I still think what I said about them being completely disjoint is technically true. Like, they could be. Never did it actually say they have to have anything in common. They just said you're trying to find regions with overlap. But there's no reason why they would have overlap at all. I guess we just assume it does. Yeah, okay, fine. I'll just stop there. There's no point getting started with that yet. I was tempted to move on to another problem instead and come back to this one, but I'll try and do it in order. So that was 1 hour and 20 minutes of reading part 1. Oh, what is part 2 going to be if this is part 1? If we're lucky, it might just be something that falls out quickly after solving part 1, because this is kind of crazy for a part 1 problem. Literally, I've never seen... I can't recall any problem of this nature where part 1 was just basically indecipherable. Alright. Well, see you next time. So the idea was, we start with node scanner 0, and then in each step we want to basically find another scanner which links up with one of our scanners that we have, and figure out how it aligns. It's a bunch of for loops and a bunch of... I think the general process, so given 2 scanners, to find if scanner 2 aligns with scanner 1, we want to find a triangle that's common to both, and such that set of rotations. Alright, so if I remember correctly, this is a bit of group theory stuff. If you look at all possible rotations in 3D space and all possible reflections, like going from positive to negative, and multiply them all together, the full possible set of transformations is like, I don't remember the name, like the orthogonal, special orthogonal group or something. And I guess it has size 24. I would hope so. And I think if we use SciPy, then we can probably get that special group of matrix rotations and use it to multiply man, it's going to be a really nested for loop. I don't know if well, I mean, it's what we have to do. It's 25 scanners. Okay. Alright. So, the first thing we want to do is, I guess we want to use SciPy. No module named distutils. What? Hang on, let me set up the Okay, oh, damn it. The interpreter's not set up correctly. I'm using Python 10. We should be using Python like... app data, local, Python. Why do you have to do all this stuff manually? Why can't you just use the latest version of Python? Where is Python? They used to install it in... They used to install app data local programs Python. App data local programs Python. App data local programs Python. There we go. Python 313. What on earth? Okay, we'll see if that works. There we go. Alright, still SciPy. That to install. Or NumPy will probably manage. I'm sure they'll both have it. Oh, let me just get my coffee as well. Installed. Okay, we got installed numpy. Still numpy just in case we need that as well. Alright, so, Sippy has, what do you normally, what abbreviation to, whatever. So we probably want to store these as I'm more familiar with numpy, let's use numpy. So we want to store these as vectors, right? So we don't want that. We want p dot array. Array. You have to cast that to a list. Yeah, okay. All right. So, the process is, so we've got a list of so trying to build recreate the what was the wording they used? All right, we'll call it region. We're trying to build the region. So region equals. So to start with, we can assume that node 0 is, everything will be based localized around scanner 0's frame of reference. So we could just put scanner 0 in. Region equals be beacons. Beacons is the wrong term. Oh no, it's called scanners. Okay. Region equals Scanners. So just take... So region is going to just be a list of these scanners, but it's always going to be in the frame of reference of 0. So we can't just add scanner 1 to it. Scanner 1 would have to be rotated. So start off with that, and I guess we want to pop 0 off, because we don't... So the idea is we keep taking stuff out of scanners and putting it in the region by rotating it correctly. And when there's nothing left in scanners, then we've basically reframed everything. That's the algorithm, essentially. So while scanners. So while there's still scanners that need to be added to the region. So our region has a list of scanners. And there's a list of scanners to be added. So we basically want to take from... God. So for scanner 1 in region, for scanner 2 in scanners. So we take 1 from the region, 1 from the scanners, and we're going to see if they match. And they match if they have 12 beacons in common. God, yeah. Does that mean we have to go through all 24 rotations right now? Probably should. Get the index as well. Huh? So now we need the special orthogonal group or whatever. I gotta Google this. Is this the one we want? Special orthogonal group is the group of all rotations in 3 spatial dimensions. It is a Lie group. That's not enough. So that's probably size 12. The orthogonal group is probably the all rotations and reflections. Okay, there we go. Right, the orthogonal group. I'm trying to find the... How many elements are in the orthogonal group? It should be 24, right? Why didn't they just tell me how many there are? SO3... O3. I'm interested in O3. Oh my god, they give you so much complex stuff, but they don't tell you how many elements are in the group. Okay. Groups ON are real compact Lie groups of dimension, blah blah blah. Two connected components. SO of N being the identity component. Yeah. How many elements does it have? That's all I want to know. I may have to do actual group theory. Labyrinth of code. That's crazy. Orthogonal group. I don't... So much stuff I don't want to know. The orthogonal group in 3D has infinite many elements. No. Orthogonal group O3. I just want data on O3. O3. Why is it so difficult to just tell me how many elements there are in the group? Just try searching for... many elements. 48 in total? Hang on. Okay, Wolfram Mathworld actually gave us an answer. O2... No, it's not the answer. It should be 24, right? It's... unit cube has 48 possible rotations and reflections. There are 24 rotational symmetries and 24 reflections. Yeah, but these are some of these are duplicates, right? So what is the 48? So why did it say 24 in the problem? How did you get... Let me have a look at the problem again. In total, each scanner could be in any of 24 different orientations. Facing positive or negative X, Y, or Z, considering any of 4 directions up from that. Ah, okay. So... Oh, we don't count reflections. We are actually using the special orthogonal group because if you can rotate. If you're facing positive X, you can just apply rotations, and then you're facing negative X. I got confused there. There's no reflections. It's just rotations. So it's a special orthogonal group of orthogonal rotations. There's 24 of them. Okay, got it. Now what? NumPy. Spell NumPy. NumPy. Special orthogonal group of matrices. And this is what we want. So we want SIPI. Return a random rotation matrix. No, we don't want that. We want all of them. Okay, do we have it in NumPy? I think we're gonna have to use SIPI. I don't want to calculate things, just give me the... I already did my degree in mathematics, I don't want to go back to that. I think we have to use SIPI then. Why wouldn't it have it NumPy? Isn't that a basic thing? Assume we're using SIPI. SIPI. I want random rotations, I just want... I should have specified 90°. That's key. All right. Yeah. No, but I know there's a method that just gives it to you straight away. Huh? numpy.90. Oh. Alright, I guess we use this. Okay. Why have you separated these? God. Put them in the same... I have to copy these in. Or, better yet, we could do... get... road... Oh, hang on. Yeah. No, do get rotation matrices. So make sure we yield the identity matrix. There we go. Let's just have a look at that. Oh god, we've got an infinite loop here. Stop. Can we make them integers? It's a matrix. Can we... integer matrices. What is this? Go back to what you had before. Okay, there's the complete code, but I want it as a... Arthur Euler axis angle degrees. Yeah, okay, can we make it into integers? Axis angle degrees. I don't know anything. Okay. As matrix is a sippy thing? We stick with numpy stuff. Yeah, I want these integers. Data type. Okay, so we want d type equals int. That'll do the I. Correct. And then this one. Can we round it? Well, I don't want... What if you use numpy.as matrix? As matrix R. Stick with numpy. How do we... God, how do we... We round it? Round. Do it like this. What? Okay, so it's not complaining there. Okay, np.round. gonna be on this for hours, and it's not. I'm not even solving the problem. I'm just messing around with stupid linear algebra. I need a crazy amount of mathematics for this problem. All right. I think the problem is this is a numpy array. What does it return? Oh, it returns a rotation. So I don't think we can just cast it to a matrix like that. We have to backtrack. So we want as, so it was as, what did they have? R dot as matrix. Okay, please work. There we go. Right, how many do we have? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why only 10? There's 3 times 3 plus 1, it's 10. What? Why haven't I got 24? Also, why are we doing... Okay, this is wrong. Angle should be 0 as well. 4 times 3, that's 12. Well, this is all single rotations. We want the group. How is this so difficult? No. I know there's a method somewhere in Sippy. Alright, we have a statistical one, which can generate random special orthogonal matrices. I don't want random, I just want all of them. How do we get all of them? I know there's a method somewhere which does this. Alright, AI is giving me a method for generating them. It's a big method, but... Why? Okay, no, hang on. We have Sippy stats special orthogonal group, so there must be a method which just generates them non-randomly. Fine, we'll just... Okay. We'll use this method then. Look at that. Okay, fine. Okay, and can we just... How do I do that again? We do dot as matrix. Wait, no, it's already as a matrix. We do mp dot round dot as type int. How do I do this again? Oh no, that is not as a matrix. I need to put that in. Now what? Oh, let's type things. Okay. Let's make sure we've got the right number here. $62 of what? How did we get 62 of them? It says 24. is also kind of expensive. I'm sure there's a faster way to do this, but whatever. Can we not just... Okay, you know what? Can we get a hard-coded list of rotations? I mean, it's just going to be... How on earth did we get 62? It's 4 times... Hello, Smab UK. Created a giant switch expression for the 24 cases. I mean, yeah, I think at this point it's easier just to literally just work them all out by hand and then hard code them in. I don't understand why this... I'm sure yesterday I found something in Sippy which actually does this, and now I forgot what it is and I can't find it now. Like, Sippy has a statistical thing which randomly generates special orthogonal group elements. I'm sure there's a method which just lists them, but... How on earth is there 62? That doesn't make sense. Okay, this thing is probably not working. Existing rot. What's existing rot? Well, existing rot in rotations. Oh, I see. Because I've fiddled about with this. But that... Okay, that might solve it. 20... Yes, 24. Perfect. Okay. That should have been a one-liner, but now we actually have the rotation matrices. Okay, now we can actually do the problem. Alright, so what was I trying to do? We've got... We take one scanner from what we've solved so far, one scanner from what needs to be added, hello, Amaro. Any progress? I spent about an hour just making a method which lists all 24 rotation matrices, but we've finally done that. There they are. I could have sworn there's just a one-liner in SciPy that does that. And I'm pretty sure there is, I just don't know what it is. So, I don't think this is even efficient either, because every time I call this, which is going to be a lot, I'm going to have to do 4 times 4 times 4. And then we've got this quadratic method, which is checking if we've repeated them, so... I don't know. Well, that's why we need to just generate the matrices at this level here, not every time we are rotating the individual vectors. So we just rotate the whole scanner list in one batch. Okay. For rot in rotation matrices. So we want the rotated scanner 2 equals, and it's going to be rot. Do you just pre-multiply by a rotation matrix? Rot times. Hope you enjoyed the snailfish numbers. One of my favorites from 2021. Yeah, that was a good problem. When was it? 18. Yeah. Yeah, it didn't take me that long, but Python's particularly good for it. Alright. So rot times that. So that's a rotated scanner. We have to test this. Just do 4. Just put that like that for now. Let me see if this looks correct. So scanner 2. Alright, so and then I'll just go to the top. Oh, okay, to the bottom. That is supposed to be the rotation of. Well, that's, yeah, this isn't gonna work. Just to. Alright, so we're saying that is a rotation of that. Oh, hang on. So there's. Wait, we don't want to print any matrices. Why are we? No, something's wrong here. We've printed the matrix. Oh. This is going to be transformed or something? Addition. It needs to be a column. Is it .t? Oh, how do you do a matrix applied to a vector? Oh, you know it's not times. That would just. Oh, it's gotta Google this. Don't even have to do it. How to use numpy matrices. Numpy. How to multiply matrix by array. Numpy dot multiply. Oh, it's Sippy where you can just do times. Oh. Oh, I see. Ah. So we shouldn't be using matrices. But we shouldn't be using the special numpy thing called matrices. We should be using just arrays. So that is a rotation. Can we change it to be an array? Okay. How do we turn a matrix into an array? Alright, let's just... What do we do if we have a matrix? I think we do... ND array. So it is a ND array already. So why can't I just do times? God, I don't understand numpy. It doesn't match how you actually write it mathematically. That's what you do, right? You do the matrix times the array transposed. That's what the array looks like. So what has it done? It's done... Well, that one was just the identity. It's done an it's done an element-wise multiplication. How do I do an actual matrix multiplication? mp.multi... Okay. This one might do it. mp.multiply. Oh, that's done multiplication as well. Dot. There we go. Alright, so that one was the identity. So Basically, we've got 24 permutations of these, including possible 180 transformations. Okay. Slowly managing to make matrices work. Okay. So, we have rotated scanner 2. Now, we're hoping one of these rotations matches. So, now that we've rotated it, it may match up with scanner 1, but it'll be translated. So we need to find a triangle for which the edge vectors set of edge vectors match up to the set of edge vectors in the rotation. If we find one, see if we can extend it to size 12. So many nested for loops here. Hello, DJ. It's going very gradually. We're making progress here, but it seems all I'm really doing is basic linear algebra operations. I haven't really tackled the actual problem. Finally, we figured out how to generate rotation matrices and multiply them by vectors. Those are supposed to be basic things you do in NumPy. Okay, so now we've been able to rotate points in space. Now what? So I'm worried that this is going to be too many layers of... So this is like 25 times 25 times 24. Okay, that's fine. We can manage that. And then... yeah, but this is the most expensive bit. This is where we're looking for triangles. So... find matching triangles. Now we could take a shortcut here. We could say if we find a triangle that matches, then we just say that's it. That it matches, and that's it. But I'm pretty sure... like, what are the chances, if it were randomly distributed, what are the chances of triangles happening to match? Probably quite low. We could extend that up to cubes and just say if it's a quadrilaterals, and let's say if we find a matching quadrilateral, then that's it. We don't have to try and make it go up to 12. I mean, looking at this data, we could just say triangles. If a triangle matches, then that's it. We're done. We'll just see what happens. Turn the AC off. Alright, let's try and find a triangle then. So, how do we do this? For A1 in I1, A1 in enumerate scanner 1 for J1 B1 A1, C1 in. That is a triangle. A1, B1, C1. So we want to compute the edges. So edge vector, so it would be AB1 equals, I guess it would be E1 minus A1. You can just do subtraction, right? Element-wise subtraction. BC1 equals C1 minus B1. AC1 equals C1 minus A1. So those are the three edges of the triangles. There's a more efficient way of doing this. Let's just start with this. Just find edges. So AB1 equals B1 minus A1. Now we look for edges in triangle 2. So it'll be similar to this, but we say for I2, A2, and then enumerate rotated scan of 2. J2, B2, 2. AB2 equals B2 minus A2. Alright. Now we say if AB1 is not, I don't know if not equal to is going to do the right thing here. I'll just have to Google that quickly. If they're different, then this is basically just not usable. So, continue. So if we get this far, we have a matching edge. So this will significantly cut down the number of times we call these next loops. So thing you can't do that. You have to do if not numpy dot array equal AB1 AB2 continue. See if this ever happens. Print AB1, AB2. Stop. Stop. Alright, there's definitely a problem here. Why are we getting zeros? AB1 equals B1 minus A1. Is that even... Okay, apparently this is how you subtract. Alright, I'm just assuming that you can just do add and subtract and stuff. Apparently you can't, so it has to be AB1 equals mp.subtract.outer B1 A1. Alright, do we ever find two that are equal? Trying every scanner. Oh god, this is taking too long. We have to do this like 25 times. So it's like 25 times 25 times 24 times 25 times 24. Oh god, it's too much. What? Just see what these look like. Wait, what are we printing here? What is this? Those don't look like... This doesn't look like the right kind of array. What is this? It's supposed to be just a single vector. Why is this a2 b2 minus a2? What? This isn't the right method. What? Why can't it just be one minus the other? Wait, did that not work? b2 minus a2. Hello, Chandu. It's not going well. It's just a huge amount of linear algebra for this problem that I'm working on. b2 minus a2. That should just be one vector minus the other. Why has it become a matrix? What? See exactly what we're doing. Okay, so we've got A is a vector, B is a vector, and I try to do B minus A, and it becomes a matrix. God, I don't know. Why can't they just make it match what you do when you're actually doing maths? One minus the other. Let me have a look at this. NumPy, pairwise subtraction. Okay, outer is clearly wrong. Outer turns it into a matrix. NumPy dot subtract. It's just dot subtract. Oh. X1, X2. Let me try that. Yeah, dot subtract. There we go. A, B, A, B. Why is it so complicated? Like, I normally just write my own vector class and I just make it override minus to do minus and plus to do plus. Okay, okay, okay. So, that subtract. Where are these zeros coming from? Okay. That is... So if they're equal, print that. Okay, so that's sort of, that looks okay. That's one triangle, and we want to see if they're the same. Why have we got zeros here? Don't tell me some of these are duplicates. Oh yeah. No, there shouldn't be duplicates. So A1, B1 starts from after I1. So they should never be the same. Ooh. No, we are getting some of the same. Why? Does that happen? Do we sometimes... get two are the same? What does that mean? It means there's two beacons at that spot? I mean, if that's true, it's not actually wrong to handle it that way. It's just like, I don't think that should happen, though. So why are we getting zeros? Yeah, so we're getting a whole bunch of zeros. So we're finding zero edges where A1 is equal to B1. Let's find where that happens and try and sort that out. If np.array.equal A1 B1 print tell me the scanner where that happens. Alright. Alright, so the first time it happened was here. 806. Which scanner is that? Should have printed the number. Scanner 0? What does it think would equal? Hang on, let's print scanner 1, print A1, B1. Get rid of this. So it thinks it thinks these two. What? That doesn't appear twice, does it? 806. No, it only appears once. I1, A1 in enumerate scanner 1. J1, B1 in enumerate scanner 1 starting from I. Wait. How exactly does this start thing work? Oh my god, that's not how it works. So if you do start, then you just add you're just changing the index, but you. I could have sworn you could do it the way I've done it. So what we actually need to do is enumerate scanner 1. I don't really want to make a slice. You shouldn't have to. You could just do. So this one is fine. This one we need to do. Either we do for J. Alright, do it like this. For J1 in range. I could have sworn there was a cleaner way of doing this. So we start from I1 plus 1. Okay, there we go. Alright. Take that out. Alright. So basically that has to be done. Here. J2 and I2 plus 1 length. Let's see if it ever finds a matching triangle. Okay, it found one. It found a whole bunch. Interesting. which is to be expected. So if it finds a bunch of triangles in if we find a bunch of triangles that match, that probably means that there's at least 12 nodes that match. Hello, Kiksate. Alright, stop. If we... Alright. So if we get this far, that means we found a matching triangle. So if we find a matching triangle, we'll just say that's enough to say that these match. So we'll say translation equals... How did you get into programming? Started using Python for mathematics when I studied mathematics. So mostly doing stuff like this, like mathematical type programming. That's how I started, at least. Then I used it also for software engineering. Translation equals... Yeah, I've worked as a software engineer and a data science engineer. And a mathematician, technically. Translation equals... Feels like I'll never land that role sometimes. Are you already in the applying stage, or are you still in education? Okay, so this is just going to be A2. It'll be A1 minus A2. Graduated from uni in December last year. They didn't really prepare me for software engineering at all. There was still education. Yeah, that's usually the case. I mean, education is mainly focused on research, because that's the purpose of it. So it is a bit of an obstacle. Alright. Translated rotated scanner 2. We add the translation for each of those. And then we've got it. Alright, I think this needs to be wrapped up as a method because it's like, this is too messy now. It doesn't seem like I'll get it soon, so I'll probably just use my IT degree for something else and maybe transition once I feel ready. Yeah, I mean, that's what a lot of people do. I mean, a lot of people also start as QAs, quality assurance engineers, and then try and change from there. Alright, we definitely need a method here. Define get matching transformed scanner. Base scanner. Candidate scanner. So this method will, given a base scanner and a candidate scanner, check if candidate scanner can be transformed to line up with base scanner, i.e. they have a triangle in common. So basically we just take all this, look at that, put it in here. So here, if we found a translated rotated scanner, then we return it. And if we go through that entire nested for loop and don't find anything, then we return none. Okay, we're getting somewhere now. So, except we need to use these terms. Do you enjoy doing maths? Yes. Yes, I do. I've always enjoyed maths. That was it was the first topic that I studied at university before I changed to study computer science. Well, my first degree was in mathematics, and then I went into computer science. I don't remember much linear algebra, though. This particular problem needs a huge amount of linear algebra. It's pretty crazy. Hopefully the next problems won't. Scanner 1, scanner 2, blah, 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 blah. Okay. And then here we say if we find a way of matching scanner 2 to scanner 1, then we if transformation is not none, then we put region.append transformation. And then we have to get rid of scanner 2 scanners. And then break out of this loop. Are we even allowed to do that? Let's just put flags here just to make sure. Alright, I don't think it's gonna like me changing stuff in the middle of a for loop, but we're breaking out of the for loop, so only integer scalar arrays can be converted to a scalar index. What? Let me look this up. Hang on. This is the wrong thing. Should be using that. But that shouldn't be the cause of the error. Yeah, no, that wasn't the cause of the error. Okay, now what? It doesn't like me adding... Alright, well, what does this look like? Don't tell me it's another matrix. Why is it look all weird? Okay, that's fine. That's an integer. Only integer scalar arrays can be converted to a scalar. Why can't you just add two things together? Oh, it's supposed to be oh god. It's supposed to be add. That's probably the issue. Okay, we found one. We find another. Okay. Nice. Now, so when this whole process completes, which will take forever, we will have a list of all beacons translated, and there'll be a lot of duplicates between them. So to find the number of beacons altogether, we just have to put them in a set. So can you put arrays in a set? I'm not sure if you can do that. P. And you put integer arrays in a set. No. So we'll need to convert it to tuple. Which is just tuple array. So for scanner in region, for array in scanner, beacons.add tuple array, then finally print length beacons. Oh god, now we have to wait a long time for this to complete. So when we do this, let's just print length of region, length of scanners, so we know what's left. So basically it's when scanners hit 0, we're done. And region will have all 25 of them. Alright, now we just let it run forever. This will take a long time. Okay, so we've got 2 scanners and there's 26 to go. Is that right? Yes, because there's 28 altogether. So those should always add to 28. 325. Now, will it get faster or slower as we go along? It shouldn't actually change at all. Oh no, it should be fastest when they're roughly the same. No. No, it should be slowest when they're roughly the same. So this is the fastest step. Because you're just comparing one scanner with everything. But when we get to the middle, it's going to be comparing like 12 to 13 with 12 to 13. Oh no. That's going to take a long time. This one's already taking a long time. Oh, this is not going to finish. $4.24. This isn't going to work. It's just going to get slower and slower. Like, they didn't tell us how it connects, so we have to try every node from the first. I don't see any way to speed this up. You need to look for triangles, because that's like the smallest... Wait, we're not even looking for triangles. We're looking for line segments. Oh man. We didn't even extend to triangles. I don't know if this is accurate enough then. So our assumption is if there's even a single line segment in common between the two... Oh, this isn't going to work, isn't it? Because it's not that uncommon for line segments to match up. But if we extend to triangles, it'll take 20 times longer. This method we could speed up just by hard coding them. I don't see... Why did I not do that? We start again, because this is basically doing 20 times the work every step. How do I do this? Just, Stop. Yeah, hard code it, and now we can go... That's gonna be 20 times faster now. Where did I use it? It was here. Yeah, we were doing that every time. Okay, do that. Frightened Swan, how can you remember all of this math stuff, or are you just thinking logically? I don't remember a lot of these maths things. I'm just kind of Googling them, looking on Wikipedia constantly. But for the most part, I'm just thinking logically along with Googling maths terms and stuff. We'll definitely need to find some performance shortcuts to make this work efficiently. My original solutions for day 19 took a minute to run before I had an epiphany. Well, let's try this now. Hopefully it runs a bit faster. So I've hard-coded the rotations. But it's still going to be quite slow. 226. Yeah, because I don't think this is even going to be correct, because I'm only using line segments, and it's pretty high chance that line segments can just happen to match. By chance. I'll just try it anyway and see what happens. It doesn't seem much faster. So we've stored the matrices. Thing is, we don't even need all 24 of these. If we're just worried about the distances, we only need half of them, really. We don't need the... Well, hang on. No, we only need 6 of them. 6 permutations of the axes. That will be enough to tell us if a triangle matches, but it won't tell us what the exact rotation is. But then once we found the triangle, we can actually find that. So maybe we don't need all these rotation matrices. So that will cut it down from 24 to 6. So it'd be an axes permutation, but that doesn't... Can you just swap the axes? Is that a valid rotation? It might not be a special orthogonal rotation. Some of those swaps might be invalid. Because I didn't do anything I would consider to be matrix calculations other than manipulating a 3D point, I'm not sure my solution is anything like yours. Yeah, I mean, the matrix calculations I'm doing really are just applying the 24 rotations to a point, a point. I don't feel like continuing this right now. I might leave it till tomorrow, but if this completes, I don't think it's going to be correct. I need to do what I just said and consider only the 6 permutations. And if we find a triangle there, then we go and find the full rotation. But so once we get to like 12, 13, yeah, it's going to take too long. I mean, it's getting somewhere, but... I can't believe this is part 1. What on earth is part 2 going to be? Scanner in region 1. Like, I've done the most general case where we don't... So we've collected a bunch of scanners, which we've already solved, and there are other scanners to be added. But I don't know which of the added scanners we should be dealing with next, so I just try all of them. But it could be that... Like the example they had, they always used the last scanner they added to find the next one, but that might have just been coincidence. Yeah, I should really just use the test data. I think this is going to take too long at this point. Yeah, if I run it on the test data, it should... duplicate, and it's coming up to 2 hours. Alright, so they added 0, then they added scanner 1. Then they added scanner 4, which connected to scanner 1. Then they added scanner 2, and they didn't say what it connected to. Then they added scanner 3, and they didn't say what that scanner connected to. So like if they went in a line, then that would cut... If they can be added in a line, then that would cut out a whole factor here, but... we don't have any such assumption. Everything could connect to scanner 0, for example. We don't necessarily need to use vectors either. We can use raw distances, Euclidean distances between. I don't think that matters though. Constant, basically constant time operations either way. Alright, we'll try the test data. The vectors will be more reliable, because many different vectors could give the same Euclidean distance. Alright. We've got just 5 scanners this time. $95. What we actually needed was 79. We've got excess beacons. But we did actually... yeah, but these are not triangles. That's the problem, isn't it? So we're adding... God. We are being too... generous in... so we're sometimes adding scanners when they weren't actually matching. And then that will give us extra beacons. So I think that will be solvable if we can solve that if we go to triangles. So what, I mean, if we've got matching line segment, then we only need to go to the next. let's try and extend this to triangles then, because this is, we're almost at that point. So now we've got a line segment which matches. We just want to extend it up to a triangle. So say for A1 in range J1, E1 equals scanner 1, A1. Okay, so that's the third point. This is adding time as well. Well, okay, we're using the test data, so now if we could take a probabilistic approach here. Like, we've got 26 25 scanners, beacons in a scanner. If 12 of them match, it's like if you just pick any you were to just pick any triangle, there's a reasonably high chance of it being amongst those 12. So if you just repeated that like a few times, pick random triangles until you're satisfied that you've picked enough. Like, if you just did that 10 times or something. The chances of it being... So we need to basically do it until we're satisfied that the chances of them not matching is like less than 10% or something. I can't be bothered to do the maths now, but maybe that would actually work. Probabilistic approach. Then we don't have to exhaust all triangles. We're basically exploiting the fact that we know that if they overlap, then half of them must overlap, basically. Half of them must be in that overlap. Half the nodes. I mean, doesn't that mean we don't even have to range over all 25 if we range over... Do they always have 25 in them? If we ranged over... like... I've mentioned multiple optimizations here. Let's just try this triangle thing and see if it works for the test data. So then we've got AB1, AB2, AC1 equals C1, A1. C2, C2, A2. And we want to say if and then let's do that again for the last edge. I don't know if that's even necessary, so it'll be B, C1, C and B. Alright, so at this point, if we reach this point, then we have a triangle that matches. And then we just go from, take the vertex A1, A2 to work out the translation. Alright, try that. It's probably going to be much slower now. But not that slow, because if we found a line segment, there's a high probability it's already part of a triangle, in which case it wouldn't take long to find the third vertex. So this is a slow approach, but I'm hoping it's accurate. If we get 89, that's a good start. 79. 79! Okay, so it's correct. So I have two choices. Either I optimize or I leave this running for days. So something I said earlier is a very easy change to make. And that's to just not go through the whole scanner one, but Alright, let's think. If 12 of them in common, if the 12 of them must be common to both, then if we have gone through all the nodes and we've left, if we've got 9 left to check, and we haven't found a triangle yet, then we already know that we're done. There can't be any match. Because if there's 9 left, then the 3 that match must have been in the ones we checked. So if there's 9 left, and that's like half of them, just less than half of them, then we just stop, right? So if length of scanner 1 minus I minus I1 is less than or equal to 9. Is that right? Yeah. Then we break. Okay, just add that. See if that still gives the right answer. Does that speed things up a bit? And we're kind of cutting that down by a half. But there's still exponential. We can't add that here because Wait, we can. We can do that in all three. We can actually just ignore the final 3 vertices fully, can't we? The final 9 vertices fully. Let me just put that thing in here. The scanners might have different length. I've never really checked their sizes, so run that again and make sure we still get the right answer. So we're basically just ignoring the final 9 vertices from scanners. Like, that went faster. And then we can even add it to the 3rd loop. That won't matter that much, though. Alright, try that. The first one took a long time, strangely, and then it gets quicker. I thought the first one would be quicker. The longest time should be when they're roughly equal. Oh, it does seem that's the longest time. I mean, all we really needed to do is just cut off the final 9 from the original. Array. Instead of this weird break condition. Why is this taking longer now? Maybe this wasn't quite correct, this bit here. We just made it impossible now. The logic should still hold. Yeah, we've just made it impossible. Why didn't that work? But we can add these here. I1. Okay, take these ones out. Or just leave them in. I don't know. See what happens now. Jammed it up. Why? I thought I was onto something here. Or should it be continue, not break? Oh yeah, the first one is break, but the next ones are continues, not breaks, because we still want to try different. Oh, damn it! Wait, no. No, it is break because we don't want to use any J1s which are in the final 9. Like if there's a triangle to be found, it should be in the first. Oh. Just change this to continues. No, that'll do to give the same result. I just take this out. We had this working thing a moment ago. It's not working. I don't know why this doesn't work. Okay, go back to this one. So we just leave that condition in, everything else. What happened? Broke it. It was working. V1 scanner. God, where did that come from? Wrong array. Has that always been there? Oh god, bad. It shouldn't have worked then. If I must have just added it recently. Get rid of these conditions then. What's happened? Oh my god. It's broken. How did I manage to break it? This should be as it was now. A1, A1 in enumerate scanner 1. G1 in range 1 plus 1. No, that should be scanner 1. Oh my god, I'm mixing everything up now. Okay. Scanner 1, scanner 1. Rotate to scanner 2, rotate to scanner 2. And this one is scanner 1. This one's rotate to scanner 2. Okay. That should be fine. Alright, so let's see if this works now. Okay, that's correct. Now the idea was to just add that in. See if that still works. That should cut it down further. So we're only looking at our line segments in the first section, and the final 9 elements are ignored. Okay, good, that's even faster. Now, for some reason it doesn't work when we take it... when we look at... It doesn't matter, but that should be scanner 1. Okay. Oh, it might matter. If the scanners are not the same length, then that matters. Okay, still working. Good. I don't think it doesn't like it if we do this. Okay, it's fine. I think it's because I mixed up the names of the scanners and then do this as well. It should just get faster and faster now because we're just always dealing with an array of size. Oh, look how fast that was. And now, in theory, we should be able to add this as well. And this. Like, this is the third point of the triangle. Yeah, okay. Okay, so basically we're just ignoring the final 9 elements of both scanners. No, we don't care about any triangle that intersects with the final 9. Oh, did this one break it? Why? Let me rotate scanner 2. Fine. For some reason we can't put that condition in. I can't imagine why. But it works if we comment that out. Okay, that's a lot faster. Could try it on the big data. I don't know if that's enough though. Let's just see how far we get. So the other thing I said was something about probabilistic. Oh, we got the transformations. Hang on. I like this idea of doing a probabilistic thing, but that means we just have to pick random triangles from each several times. And if we do it like 10 times and we still don't find a match, maybe we can say with quite high probability that they're not overlapping. That makes sense. And it should, in theory, be faster than doing this exhaustive search, but... 5:23. I mean, it was making progress now, but the worst is going to come at 12:13. Um, 6:22. Well, this might actually run. Take a long time, but it might be all we need. Like, what else am I going to do? There's a probabilistic approach, or you don't even have to try random triangles. You could just try a bunch of random lines, and if a certain percentage of them have matches, then well, then you can say quite likely. I can tell you part 1 takes about 170 milliseconds on my machine. It looks like we might actually get there in the end. 7:21. I don't know how much longer these last. 12:13. If that actually runs in a reasonable time, then we're good. But yeah, this is definitely a slow approach. I guess we're doing these rotations over and over again like we've done before. Like, we should just have a method which caches all the rotations of all the scanners, so that I never have to do that again. D20. Come on, come on. God, part 2 is at the very least gonna just take this whole length of time again. uh, I don't know. I can't think of any major. Definitely storing all the rotations of all the. Oh, what was that thing I said? For working out whether a triangle of distances is common to both, you don't need all 24 orthogonal matrices. You just need the 6 permutations of the axes, because and then that'll tell you there is a common triangle. And then once you know that, then you can use the 24 rotations to well. Yeah, because we're ordering them. We're saying A, B, and C has to match A, B, and C in this specific order, which is just a bit. We don't need to do it that way. We can just say A, B, and C could match B, C, A, or minus A, minus C, B, or whatever. So we don't have to have this much depth in the for loops. We can look for permutations. That should make it like 4 times faster, really. Oh no, 12 is not the midpoint. It's 14 is the midpoint. Oh, it's going to take even longer. So we'll get to 1020. The worst one will be 1414. Hmm. I just realized that we didn't need to do it this way. I should have just tried node 0 against everything, added all the ones that matched, and then we never have to touch node 0 again. everything will just be matched to 1, 2, 3, and so on. Well, that's way faster. Hang on. But still... No, it's not. It's still quadratic. Hang on. It is faster because we're not repeating. If we know that node 0 doesn't match with... It's faster, but it's not hugely faster. It's just, it probably would save a bit of time. It's still quadratic, but it's just we're not repeating pairs of scanners we've already done before. Yeah, it probably. I mean, how quickly could I do that? I'm not going to stop the process now, but I guess it's just if we just put like a hash set and say if 0 has been matched with 3 before, whatever, then just put that in the hash set so we don't try to compute that again. Or we just use the Python built-in cache. This would yield a fixed result given that scanner and that scanner. So just cache it. So that if we that, and that's slightly slower than just not doing that pair again, but it's an easier way of doing it. So that would be like cache. Try that afterwards. It might be much faster. Well, 16. Yeah, I think caching that will be improvement. Should like halve the time at least. Which means there's still time to do it. Oh. We'll stop the process at this point. 13, 15. I don't understand why this broke it though. This line here, it's the same reasoning as above. If we cut off the final 9 nodes from each, then we should still have a triangle in common. Like in the worst case, we've cut off the other 9 matching nodes. So the 3 that are left would still form a triangle. But then why can't that? Why did that not work for the 3rd point of the triangle? Gee. I mean, that worked here. So why did that not work for the 3rd vertex of the 2nd triangle? Why was it okay for every other vertex and not this one? That is odd. Yeah, that's almost indicative of a bug of some sort, which is a bit worrying. Like, it should hold for that. So am I doing something differently for that specific vertex? Alright, we're on 14, 14. We're over the hill. It should be exactly as slow. In the final half, I guess. Do the same thing. No, it should be faster. Because the rotations have already been applied to the ones we've stored. So that means we have fewer scanners which need all 24 rotations for them. So it should get faster from now on. Hopefully. Because we no longer need to try 24 rotations. Or... Oh, no, it should be this. No, I think it'll still be the same length of time. Because it's not a very smart for loop. That's why we needed caching. We go up to 3 hours. I'm gonna have to stitch the video together, and it's gonna be like 4.5 hours of me just not doing anything. 13. God, if this doesn't work, then I'll have to try those other ideas. I know. Oh God, we'll take a look at part 2, but if it's anything beyond something that falls out quickly from what we have, then I don't want to worry about it right now. fast forward through the staring at the code. I mean, I've been tempted to edit my videos, but for posterity, I've always kept in all the downtime. I think the worst cases I've had were like 6-7 hours. Fairly quick to go from part 1 to 2. Well, I probably should have printed out all the beacons or something, because if I needed them, I'm gonna have to rerun this. Yeah, I should have just printed out all the translations and all the beacons. That's all the information needed to rebuild everything. Yeah, that does happen. Yeah, so here, before I even do any rotations, before I do that, I should have just tried the triangles thing and just check if a triangle edgewise matches a triangle edgewise in the other, independent of the axis, independent of directions. Could even use Euclidean distances, but there's no reason to. I think just using the vector is fine. But we ignore signs and permutations. So that'll be a lot quicker. And if it's a yes, then we can do all this, I guess. That will rule out the negative cases faster. 10. Gradually getting faster. I mean, like if you didn't bother computing what the rotations are and stuff, and you're just trying to directly find the number of beacons, it would basically be, well, it would be like the inclusion-exclusion principle. It would be the sum of all the lists of beacons in the scanners minus all the intersections. But finding intersections itself is the problem. But if we took that approach, no, because there might be lots of intersections between scanners. Yeah, like small numbers of intersections, like 1 or 2 of them. That doesn't really. I never really used the fact that it's within 1000. Like, that imposes a cap on the amount of transformation you make. Like, you could take a different approach and Um, I mean, a number of transformations you would need is like 1 billion, but if you just went for like just X and Y transformations, it'd be like 1 million. And if you tried all rotations and XY sorry, not transformations, translations. If you tried all rotations and XY translations, that would be like I don't know, 24 million or something. Maybe a bit more because there's negative 1,000 as well. So I don't know, like let's say 50 million. Oh, but that's for one pair of scanners. We're basically just doing the same amount of work. Well, I don't know. I mean, you don't even need to do 2 dimensions. You just do 1 dimension. If you did 24 rotations, try all X translations, and if you find such a combination that you've got like 12 nodes matching, I mean, that's it, isn't it? That would give you. Then you could probably just say, okay, those 2 match up. Unless he's thrown in some traps in the data, but I don't think he has. So that would be 24 times 2,000 to compare 2 scanners to see if they match up or not. Maybe that's really the way to go about it. Like the cap of 1,000 to negative 1,000 is actually smaller than I realized. So ranging over translations rather than permutations of all 3 axes. But basically projecting everything onto the x-axis and solving the problem in 1 dimension. I think that might be the way to go. And you can also project them to the y-axis and solve there too if you just want to rule out any yeah, you could separately do that for the x, y, and z. Each would take like 24,000 or whatever operations. And if you get a yes in all 3, like as in there are 12 in common in all 3 axes, you don't need to check that they are the same 12. Then you'd be pretty confident, wouldn't you? Huh. I think that's probably the better way to do it. So it's like 24,000, but then you got to do the whole list of scanners, so it'll be like 1,000 times another 24. It's like 500,000, and that's you do that for each pair of scanners, but not each pair of scanners. It'd be pair of ordered pair of scanners. So like half the full pairs of scanners. So several million operations. Yeah, I think that is actually the better approach here. Completely turn it on its head. Range over translations. And even then, you don't have to do all 12. You can just look for like 6 or whatever. Well, no, I mean, when you find a translation and a rotation, you can just apply it to the whole list of 25, and then you'll immediately see how many match. See, so, Alright, if this doesn't work, I'm doing that. It'll be so much cleaner to code as well. This is grotesque. Yeah, at first I thought a cube of size 2000 by 2000. 2000 is just too many values, but it's actually not. Well, no, 2000 by 2000 by 2000 is a lot of values. But you just look at the axes independently and the axes are independent problems, aren't they? Like, if you find the translation that works for X, well, the rotation would have... You might need to apply the rotations first. So you try all... So for each permutation, each of the 24 rotations, you then project into X, Y, and Z, solve those problems independently, and that would give you... Each would give you the translation of X, the Y, and the Z separately, instead of combining all three. Because you can just add on the translation. Just shouldn't, like... Whatever you translate X by, it shouldn't affect Y. Ah. If we get the right answer here, though, we don't have to worry about that, but... It seems like this was probably the hardest day of the month, going by the number of people solving it and the time it took people to solve it. The leaderboard. Oh, 25-3. Come on, we're so close. It shouldn't take this long for these ones. Don't get stuck. Theory, it could get stuck in an infinite loop here if it doesn't find a scanner to add. Hope that's not what's happening. How could that happen? That would happen if... this process just didn't find... Like, every scanner must be connected to the region. Like, that was sort of implied by the description. So every scanner must have some other scanner for which it has 12 in common. Which would also imply that there is a triangle in common. We know Eric is tricky with his data, so I wouldn't put it past him. the data, yes, but the description, I mean, the wording was not great, but the description, as I understood it, seemed to imply that it forms it should all form a region because, what's the sentence I'm going off? It says, scanners and beacons map a single contiguous 3D region. Contiguous to me means that they're all connected. Yeah, because if it was two separate lines of scanners, it wouldn't be a single contiguous 3D region. It would be two contiguous 3D regions. So I think that should mean that... God, it's stuck, isn't it? Should mean that every scanner overlaps with something, otherwise it forms its own separate 3D region, or at least it's indeterminate, and no longer be a single contiguous 3D region. The wording is just kind of vague. This region can be reconstructed by finding pairs of scanners that have overlapping detection regions. So it's asserting that this process should build the whole region, such that there are at least 12 beacons that both scanners detect within the overlap. By establishing 12 common beacons, you can precisely determine where the scanners are relative to each other, allowing you to reconstruct the beacon map one scan at a time. So it's sort of forcing certain properties of data to be true for this to even make sense. But I don't know. Okay, so we're stuck on 25.3. I should have stored the beacons and stuff. Which means there's 3 scanners to add. I'm pretty sure we're in an infinite loop now. And we can't find any way to add any of these 3 to our 25. If my code is correct, then, I mean, wouldn't that mean it's not a contiguous region anymore? I think next time I've got to try that other approach, just project onto the X, Y, and Z axes separately, solve the separate problems. It'll be so much easier to code. Man, I need a nap now. Staring at this IDE is for so long has been making me tired. Yeah, this is not working. And it kind of makes sense that it failed here, like towards the end, because basically those 3 that can't be added, they may have been found early on, but we couldn't find anything to add them in, so they just kept on coming up and up again and again until they're the only 3 left. So many vague points in this description. I still think that contiguous 3D region implies that they must all connect. Wait, so the example he had... Alright, it doesn't matter. We'll leave this till next time. I don't know if I'll even do it tomorrow. I might need to do some prep. Otherwise, we're gonna end up with like a 7-hour YouTube video, which wouldn't be the first time, but today is one of those days where my code is nothing like yours. Yeah. I think tomorrow's code will be nothing like today's. I'm going to completely rewrite it. Range over translations instead of triangle rotations. Now I'm trying to work out if this even is correct, this thing I did about cutting off the final 9 elements. So we're saying 12 points must match. Therefore, if we just cut off 9 from each of those, then there still must be 3 that match. At least. Something seems a bit off about the way I've done it, though. I mean, it's equivalent to saying if... Oh... I see the flaw now. We're not cutting out the same 9 in each of the scanner lists. We're cutting out a different 9. Ah, okay. Damn it. So you can't do it for both scanner lists. You could do it for the first one. First one, you can say, okay, if there's a triangle that matches, then it must be in the. Then if we get to the final 9 and we still haven't found it, then we haven't found it. That's sound. We can do that. Everywhere else, we can't do that because it may not be the same. Oh, damn it! So it has to be like that. You can't do this. You can only do that for the very first loop, because they're not necessarily the same points. And that's why that was breaking it, because it's not actually a valid assumption. We just got lucky with the test data. Let's see how long this takes, how fast this runs now, because I'm caching it. list. Just make it a tuple then, because we're not changing it. Oh, we are changing it. An individual scanner can be a tuple. That should be a tuple. Where are you getting more lists from? Ah! No, because we did change it to... Yeah, that needs to be a tuple as well. Unhashable type. Oh, damn it, you can't hash in numpy arrays. Let me hash them. Can I rewrite the numpy array definition on the spot? Alright, another way we could do this is just say region equals 0. To remaining equals region. So now it's just numbers, and here we fetch them. So now it's just hashing indices, and then when we pass these in, we have to say done equals false. For, let's say, S1 in region, to enumerate scanners to be. So this is going to be remaining. Oh, damn it. Then we need to handle the transformations. Okay. We just redefine the scanner. Like, we don't need what it looked like before. We don't need, So we just change how it was defined. So scanner. Scanners S2 equals transformation region dot end S2 delete remaining I. Okay, let's see if that's any faster. Probably not. But this will speed up because we're caching. Let's just see what happens. But it's not going to speed up by much. It might halve. But we've also taken out all these shortcuts which were invalid anyway. So yeah, it's not. No, yeah. Let's leave it till next. At the very least, let's just make sure this still works in the test data. So we are caching, but that only avoids some duplicates. Oh, while scanning. No, it's supposed to be while maining. Alright. If this is correct, then I'll just worry about this next time. And if it's not correct, I'll also just worry about it next time, but that just means there's more to worry about. Great. Oh. Just keep a dictionary of scanners now. And re-update them when we get the right transformation. $79. Now so this would, I think, will give me the right answer, but it'll take forever to run. I could just run it offline for a long time and just call it a day. Offline and then just do a stream where I pull up the answer and then look at part 2. I don't know. So let's see how long it takes to get to 3, 4. I mean, this should be correct now because, yeah, we're not ruling out. We just got that one shortcut condition here. Well, I mean, not necessarily correct though, because there could be triangles which match but don't actually correspond to 12 matching vertices. He absolutely could have done that. That's another whole problem. Uh, Coming up to 4 hours now. This is going to be the most boring of all my Appins of Code YouTube videos. I can't think of any that were quite as uneventful. Like, there was one or two which took 7 hours, but I was doing stuff in those. Even pulling out Microsoft Paint and sketching things. Oh, it's speeding up. It's actually going faster. Let's see where it goes. No, it's not really speeding up, is it? Because we should be reaching the point where we're... where we're ruling out all those things. The more things we have in region, the more things we have cached that we don't need to repeat. So we should only be running like... Oh, this one's taking ages. I mean, that one went quickly, I guess, because it just found one early, that's all. Okay, 523 is taking longer than I would expect it to. So maybe the data is a bit tricky, which is all the more reason to use that other approach. Like, so I'm looking for triangles in one set, looking for triangles in another set, and seeing if they match. It might make more sense if we settle on a triangle from the first one, and then and then I don't know, 22. I mean, then we could project the triangle onto the x-axis, and then try and find that projected triangle in the projection of the other one. But this just comes back to projection. We might as well just go with the other approach. I can't tell if this is going to speed up or just take roughly the same amount of time. It should speed up because there's fewer things on the right to check, and we're ruling out things from the left if they've already been tried against several of the remaining things before. Yeah, it looks like it might actually speed up. So in general, we would just be looking at like maybe 2 or 3 things from the left-hand side every time, because eventually we'll reach. There's definitely at least one awkward case I hadn't considered when I passed the first tests, as I have a commit where tests pass. Uh-huh. So this should, in theory, speed up, because then we have fewer things on the right to check against, and we would hope that maybe the majority of the things on the left are exhausted and cached away. This might actually work, but oh, 8:20 went by in a flash. That's good. Sometimes it just goes by quickly. So it's like it was probably the 8th thing that got added just matched up with whatever was next in the remaining set. I think this will be fine. And if it's correct, then... Oh man, I forgot to add in and just like print the beacons. Probably need them. I should have cached the rotations of the scanners as well. But there should be a method with which, given the rotation, actually it doesn't have to be caching. It can just be a full table of all possible rotations of all scanners. Then it's just a lookup table. And you look up the list of rotated set of scanners, because we're doing those rotations every time. I wonder if this could be done as a sort of exponential growth thing. So like, you find a pair of nodes which connect, then you find some other pair of nodes which connect, and then you've got 2 disjoint pairs, and now but you only need to apply 1 search to connect those 2 sets. So you could sort of double this each time, and you wouldn't need as many instead of tacking on one scanner at a time, I think you can sort of build up sets of scanners which connect separately, and then when you combine them, all you have to do is find one node they combine on, and then you've got the rotation for the entire set. That's interesting. So that might actually be a lot quicker, because instead of linear growth, instead of linear growth in the size of your completed scanners, it's actually exponential, isn't it? Essentially doubling your sizes with only one check. It's like a quicksort type thing. Alright, well, I have faith. 16. Yeah, I think the best approach really is just anything that takes advantage of projecting onto the X, Y, or Z axis independently. Whether it be at the very start or after you've computed a triangle or something. $14.14. See if it gets faster now. I never pasted an answer into the site yet. Yeah, because I never got a final number. Whoa! Okay, 1711. It's getting faster. 1810. 99. Yeah, caching actually does more than half the time, because you're sort of halving each side. Well, not... It's reducing the exponent. It doesn't become fully quadratic. It sort of behaves like it's... somewhere between linear and quadratic. The 8, come on, it shouldn't take long now. You're just checking against 8 things. $21.7. 23.5. $4.4. Yeah, this has got to be the longest part 1 I've ever done these. Well, it could be... There could be one other problem that's close, maybe. Why is 24.4 taking a long time? Come on. There's just 4 things left. I mean, instead of region being several scanners, it should just be one scanner where I'm just actually just merging the beacons in. It would add more beacons to the mix, but it also removes beacons because then it's just ironing out the duplicates. So overall, it will probably be better than... Oh, but wait, the 12 thing would no longer... It would still be 12 in common... I'm sure if it was still hold. 359? Feels like a smallish number. Well, no, that sounds about right, I guess. That's correct. 359. Sometimes it's a good idea to appreciate just how big the ocean is. Using the Manhattan distance, how far apart do the scanners get? sake, I should have stored all the scanner data. Largest Manhattan distance between any two scanners. God, I don't want to run this again. Wait, so let's... Do I have what I need? Yeah, I think so. So we would just need to... well, the largest Manhattan distance between any... Okay, so we just need to store the... Wait, how do we work out where the scanners are? Oh, there is 0, 0, of course. So we just need the Alright, I think I might do that one offline, and just maybe once I've written the remaining code. I mean, we just need to basically we just need to make a list of scanner pause, and I can't be bothered to do it now, but basically we make a list of the scanner positions, and we can find each scanner position the moment it gets added to region by just taking 0, 0 and applying the transformation. And then just run this process again, and we'll have a list of the scanners, and then just do a quadratic search to find the largest distance between them. I think I'll just do that one offline. Or at least I could write the code now, I suppose, and then that the actual code is in the video. So we need to... So scanner pause equals so the first scanner is 0, 0, 0, so it's going to be that. And then while we do this, every time we add to the region, we also it will have to be done in this method. When we find the rotated scanner, we just have to add the translation in. Scanner pause dot append that translation. It doesn't even matter which way it is. We'll get the Manhattan distance. Or it does matter which way it is when we're comparing with the other ones. But yeah, relatively, that's the right translation. And at the end, we have scanner pause. So for largest distance equals 0, For A in scanner, pause. For B in scanner, pause. Largest distance equals max. Largest distance. Distance is the L2, the L1 norm. How do you put that in numpy? Not the dot product, is it? Numpy L1 norm. L1 distance. In ouch dot norm. This. MP dot sum, MP dot absolute value A minus B. Is this what they asked for? Largest Manhattan distance between any two scanners, yeah, and that includes 0, 0. Test it on the input, then the test data. So we're expecting 3, 6, 2, 1. Yes, okay. So it remains for me to write it on that. I could. Welcome back. So, it's me from the past. I ran the code and got an answer. Took the same length of time it did before. Basically doing the same thing. But we got the largest distance. Let's check if it's correct. Yes, thank goodness, because I didn't really want to have to fix that right now. That's it. 19's done. So yeah, overall it was not a good problem for me. I sort of get it now, but I partly, I don't think it was worded well. I think it was actually poorly worded. Could have used some more precise mathematical language here to make it clear what is going on here, because I thought some of these paragraphs were just completely vague and could mean different things. So that's one complaint. The other, oh no, that's the only complaint. Like, now that I understand the problem, it's actually a decent problem. I just wouldn't have worded. I would have worded it better than this using mathematical language. Anyway, I think had I gone with the projection approach, where you project into the x, y, and z axes and solve the one-dimensional case before moving up to the 2 or 3 dimensions, I reckon that would have solved it really quickly. It's probably the way to go. And I don't really want to. I'm not going to bother doing that now. But yeah, next time I'm just taking a sneak peek. Something to do with a pixel image, pixel art, ASCII art even. Okay, that will be next time. Tomorrow. I gotta go to bed now. And I gotta stitch together this 6-hour video or so. Alright, see you next time. Bye bye.